Okay, in this second part of the class today, we're going to be working with R. We're going to be doing different exercises with R. We're going to be computing different linear regressions, understanding what are the functions that allow us to compute linear regressions, what are the functions that allow us to do that, how do we work with different data sets, how do we understand what's the intercept, what's the slope, and then how do we deal with overfitting, and how do we deal with lasso and reach regularizations to avoid overfitting in our methods. Okay? Okay, so for the first exercises, to start working with linear regressions, and again, before we start, let me emphasize this. What we've seen in the first part of the class, again, is what's going on behind the curtains, okay? What's going on behind the scenes. Right now, what we're going to do in R is just execute different packages for linear regressions, for lasso regularizations. We're going to be testing all the things that we have explained there. We are not going to be looking into the math behind, okay? So all the discussions that we had regarding how do we fit a model, minimizing the error or maximizing the likelihood, and so on, those are things that are internally executed by the commands that we are going to be running, okay? But it's, again, very important that you understand every time you write a command in R, it's very important that you understand what's going on behind the scenes. And that's the reason why you really need to understand those slides. Okay, so let's start. As we've seen already in several of the previous classes, R has a fantastic, super rich library with different datasets. So in this case, we're going to be using one of the datasets called Faithful. And Faithful has information regarding the eruption time and the waiting time until a next eruption happens for the Faithful in Yellowstone, sorry. It's going to give you the eruption time, and it's going to give you how much do you need to wait until the next eruption happens. So let's go into R. Okay, let's do exactly what you see in there. So the first thing we're going to do is basically load the library datasets, and we are going to be using the Faithful data. Okay, you can always write view Faithful to take a look at the data. As I was saying, this is a data set for Faithful in Yellowstone, so it says when the eruption happens and the waiting time until next eruption. What we were trying to do here, the first thing that we were trying to do is, something that I didn't mention. So every time you want to access one of the columns, remember that you can access them with Faithful $sign eruption or Faithful $sign waiting. But there's a shortcut. If you use the command attach Faithful, what this means is that you'll be able to use directly the names of the columns without the need to use the $sign. Okay. So if you write something like Faithful $eruptions, you get this. But now you can just write eruptions, okay, and you get the same thing. It's just the first column. If you don't write attach, you won't be able to directly get the data with just eruptions. So the first thing we're going to do is basically plot the eruptions column with respect to the waiting time, and we are gonna label x as the eruption time. We're gonna label y as waiting time, and then we're gonna put each dot of around 16. If you take a look at the plot that we have here, basically what you can see here is on the y-axis, on the x-axis you can see the eruption time, on the y-axis you can see the waiting time. Okay, this is the data that we're gonna be working with. Okay, so next what we want to do is try and see, okay, can we predict, basically, given that we see this function here with x versus y, we can sort of imagine that this is kind of linearly related, right? The larger the eruption time is, the longer the waiting time appears to be. But we don't know it. So what we're going to do is, compute the linear regression between the two. So we want to be able to see whether we can predict the waiting time until the next eruption with the eruption time. So the way we do this, we're going to call the result fitlm, and the function to compute a linear regression in R is lm. You have to write, sorry, you have to write the name of the dependent variable, the variable that you want to predict. You can check what I'm typing here is exactly what it's on the slide. So the weighting versus the eruption time. Okay, if you take a look at the model, so what you're saying here is, can you fit a model that predicts weighting with respect to the eruption time? And if you take a look at fitlm, what fitlm is going to tell you is that you know the value for the intercept and the value for the coefficient. Okay, this is the coefficient for the eruptions feature, and this is the intercept. Okay. What else can we look into? So we can also look into, okay, so this is basically the fit that we found with the intercept and the coefficient. Okay. So what we can do is that we can plot the line. So let's plot the line that represents that fit with the function upline, which allows us to plot that. We can choose a color, for example, red, and width, for example, 3. And what we are plotting here, it's basically the line for the fit. Okay, with upline, we say plot the line represented by this function with that color and that width. Okay, the line width. And as you can see here, you know, the line is representing the data not that bad. Okay, it's not exactly a line, but you know, I mean, we can kind of represent that data. Now, if we can use, this is the model that we have used, right, to train it. If we want to make a function to predict it, basically, how would the function look like? So the function would look like the intercept plus the coefficient multiplied by the eruption. Okay, so if we want to build a function, the way we would build it, it would be something like, okay, we want to build a predictive function, so let's call it faithful fit. Let's define a function. The way we create a function in R is with the command function x, and then now you can write, let's look at the slides, okay? You can create that with the function x, and then what you can do is specify, you know, what are the coefficients for the function, the value for that function. So in our case, it would be the coefficient 1, the intercept, and the coefficient 2 multiplied by x. So in this case, we will build a function which is basically the intercept, or coefficient 1, plus coefficient 2, multiplied by x. That's the function that we want to define. Okay, again, this is fx, the usual fx of theta plus theta 1 multiplied by x. This is what we are building here. So faithful is defined as a function, which is going to be the intercept plus the coefficient multiplied by x. Okay, and in this case, say that we want to predict what's going to be the waiting time given a set of different eruption times. So what we can do is a couple of things, okay? So what we can do is basically, once we have the function defined, we can define, you know, the set of values for which we want to predict the outcome. And then what we can do is, okay, use faithful fit and predict on those values. So we're going to use the function, the prediction function, to predict on those values, okay? So first we define, again, the set of values x for which we want to predict. So let's write the same values as the example there. So we want to have 2, 2.7, 3.8, and 4.9. So these are the x values for which we want to predict y. We don't know what's the waiting time. We want to use the function that we created, the faithful fit that we've created. We want to use it to predict what are going to be the waiting times given those eruption times. So we can use the function faithful fit and then give as input the predicates that we just created. And what these values are telling us, those are the values, those are the waiting times for these eruption times given this function that we've just created. Okay, we don't exactly know what's the truth. What this function is doing is predicting. So we're using the red line to approximate, you know, what the waiting times are going to be. So imagine, for example, for 2, if you take x2, what we're doing here is for x2, we are going up to the line, and it's saying the value here on the red line is 54, which is approximately true, right? If you take, say, 4.9, almost 5 here, we are going all the way up and seeing the red line, what's the y value that it's taking, which is 86. That's exactly what we're doing here. Okay, so this is an example of how we can use a data set to basically train and create a predictive function, and then use the predictive function to get or to predict new values. The way this is done internally, when we use LM internally, R is basically looking to minimize the squared error and find the intercept and the coefficients that best minimize that error.
Okay, so let's move on to another example. I'm going to be talking now of an example in which we will use the file production.txt. What that file represents is a set of points characterizing the number of products produced in a factory, which is run size, and then the number of units of time that producing those products took. Okay, so for example, for the first line, there were 175 products produced in the factory, and it took 195 units of time. We're going to be mostly focusing on training and testing linear regressions to predict runtime based on run size. Okay, we're going to be looking at feeder values. We're going to be looking at predictions. We're going to be looking at the residuals or the errors. But before we do that, I wanted to briefly mention that this is a very specific file in that the first line of the file, if you open it, does not have any data points, but rather it has the names of the columns, right? So I'm using a very specific command here to read the file, which is read table. And what read table allows you to do is, after specifying the name of the file, it allows you to say that, this is a file that has a header, and so do not consider the first line as part of the data that we're going to analyze, right? Because if you were to run a linear model with case, runtime, and run size, those are not numbers, and you would get an error. Okay, so whenever you have this type of file where the first row has names of columns, just make sure that you read it as a table, so that internally R knows that the first line should not be used for any types of computation.
If we take a look at this data set, production, okay, what production has, as I was saying, is different cases. We see what's the running time and what's the run size. So how many products were produced at that given time. And what we want to do, again, in order to be able to use just the column names, what I was saying before is that, if you write something like production runtime, you will get access to the first column, okay? But if you write something like runtime, it doesn't know what exactly is. So if you want to just use runtime, you need to attach the production data frame. If you attach the production data frame, now you write runtime, and it exactly knows that you're referring to the first column. So if we plot again, the first thing that you need to do before computing any linear regression is just try to plot what you want to predict versus the predictors, and just try to see the relationship. So in this case, we want to predict the running time with respect to the run size, right? And so what you can observe here is that, this is the running size versus the running time. So in general, you can kind of observe that whenever the size is larger, the running time tends to also be larger. Okay, in order to test that, what you can do is, let's now try to build a regression with that. So we use what's the running time with respect to running size. Okay, and this is basically the linear regression that we have computed. Okay, so this linear regression, if you write production.lm, basically has fitted an intercept and has fitted a coefficient value for run size. Now, we can compare the fitted values with the residual values. Okay, so you can take, the fitted values, you can take the residual values, and just build a data frame and try to compare them. So what that command here is doing, what this command is doing, is that it's basically taking, the production values, take the fitted value, which is basically taking the fitted values from the function, taking the residual values, which is taking the residual values from that fit function, okay, and it's building a data frame with them. And what we're doing is comparing, this is the running time, this is the running size, this is the fitted value, and this is the residual. Just let's take a look at what fitted and residual do. So the command fitted, what the command fitted does is that it basically gives you the output for all the fitted values, okay? And what the command residual does is that it gives you the residual for all the fitted values. So what's the difference between the actual value and the fitted value, okay? So this is just what we're doing here. We can also compute the residual values by hand, okay? Why do that? In fact, if we have a function which is residual, in fact, it doesn't have any sense. So there's no need to do that. But in case you are curious about, how that would actually be done, you can compute that manually. And I'm giving here the example. So the way we compute the residual values is by computing the difference between the actual running time and the running time that the predictive function gives you. So what you have here is the actual running time is here, taken from the table. And then here, the production multiplied by coefficient 1, production multiplied by coefficient 2 by running size is the fitted function. Okay, so this is the intercept, coefficient 1. Coefficient 2 is the slope, and run size is the variable, the x variable, the independent variable. And what you're doing here is, in a for loop, you are computing the difference between each of those values and basically outputting it. Those are the residuals computed manually, which is exactly the same thing as using the resid function on a given fitted value. Okay. We also mentioned that linear regressions and predictions work under the assumption that the errors follow a normal distribution. The distribution of errors, the distance between the fitted and the actual values, follow a normal distribution. So that's also something that we need to check whenever we are working with our data. Okay, in order to do that, there's a really easy check. We can use a couple of functions in R, which are called QQnorm and QQline. Okay, QQnorm basically computes the quantile-quantile plot. Okay, and basically, if the data that you are plotting in a QQ plot follows a Gaussian distribution, you need to see a line in that distribution. And what QQline does is that it adds a line to the QQ norm. So you plot the data, you plot a line, and if you see that the data is really near, close to the line, then you can assume normality of the errors. And then we can go ahead with the linear regressions. Okay? So what you need to do in order to understand whether using linear regressions is correct is just using the QQnorm and QQline commands on the residuals of the function. Let's do that. Again, the residuals are here, so what we need to do is basically to run QQnorm on the residuals, which is going to give you the QQ plot. Okay, this is the QQ plot. If it follows a line, as I was saying, like a linear regression line, that means that the errors follow a Gaussian distribution. So the good thing to do, recommended thing to do, is to plot a line. So you execute the QQ command to see the normal QQ plot, and then you plot a line. Okay, if the residuals are close to that line, it means that the residuals follow a normal distribution. And then, of course, similarly to the previous example, another thing that we can do is, okay, we have this model, the production.lm model, which is basically, the predictive model that we have, and now we want to use it to predict new values. So it's, again, similar to the example that we saw before, but in this case, we're going to use, a couple of different nuances that might be interesting. So the first thing that we're going to do is to create the data that we want to predict, okay, the different running sizes. We want to predict the running times. Okay, so to create that new data, we're going to use the sec command, which we already used in I think that the previous class, in class 3. Remember that it generates a sequence of values and then you can specify the step. So in this case, what we are doing is create a sequence of values between 55 and 345 in steps of 10 by 10. So we're not specifying how many values we want, but rather that we want them to be in 10 by 10. So 55, 65, 75, and so on. Until 345. That's going to be the data that we want to predict. And then what we are going to do is basically predict what are the values. Okay, so instead of building our own function and predicting them, Another way of doing it is using the predict function. We're doing exactly the same thing that we did with faithful, but with different functions so that you learn different ways of doing things. Okay, so you can use the predict function on the model that you have fitted and the new data that you have created and see, the results that you get. So let's go and do that. So I was saying the first thing that we are going to do is create the new data. So we are going to create, spread frame. That's going to be a new data frame. And the new data frame is going to have run size values extracted from a sequence from 55 to 345, 10 by 10. So if you take a look at this frame, it's going to be, it has 30 different values in 10 by 10. And then what we do is that we're going to predict, we use the function predict, using the production.lm model that we have and using as new data the spread frame data that we have created. Okay. So here, what you see there are the values that we have predicted. So for each of the different running sizes that we have created, these are the running times that our function has predicted. Another interesting concept when we look into regressions is the concept of confidence and prediction bands. These representations are generally added to graphical representations of regression analysis. So, for example, remember the representation that we showed with run time versus run size, where we have all the different points. We could add, and we had also the line with the actual linear regression. So on that plot, we could add confidence and prediction bands. We will see in a minute an example about that, but what's the theory behind those types of bands? So basically, confidence bands are used in a statistical analysis to represent the uncertainty of an estimate. So in other words, confidence bands in regressions will basically represent or delimit what are the boundaries where all the different possible regression models that we could come up with lie. Okay, remember that when we are using data sets for training and testing, those data sets are just a small sample of the population that they represent, right? If we were to subsample new data sets, we would probably train a slightly different model. What the confidence bands represents is basically what are the boundaries of those other models that we could obtain given that we were to change the training data set. And what the confidence bands is also telling us is that we can be 95% confident that within the two confidence bands, there is going to be the true best fit for the linear regression. Okay, so the linear regression line that represents the best fit is definitely going to be within those confidence bands. So as we train different models with different data sets from the same population, those fits, those linear regressions are always going to be within these two confidence bands. On the other hand, prediction bands are used in a statistical analysis to represent the uncertainty about the value of a new data point. Okay, specifically for regressions, what this means is that prediction bands are going to delimit the area where you can expect that 95% of all the predicted data points are going to be within. Okay, so again, we are testing our models for a specific data set, but we could test it with a different data set, assuming that, we are sampling from the same population. And so given these new points, what would be the spread of those points with respect to the linear regression? And what the prediction bands are going to do is that they're going to identify the boundaries within which those predicted points are always going to lie. And as a result, obviously, prediction bands are always wider than confidence bands. Given those two definitions for confidence and prediction bands, how can we represent them graphically? So we need to do two things. The first thing is that we need to recompute the predict commands using the production LM model and the new data frame that we created. But in this case, we need to specify another feature, which is C, or P, characterizing whether we want to compute the confidence or the prediction bands for the production LM model, okay? And so once we rerun this predict command with that option, then the outcome of those commands basically are used as input to another command which is called matline. And matlines is a command that is going to represent the boundaries that the confidence and prediction bands represent. Okay, and so for math lines, you need to input both the data that you used for the prediction, but also the confidence and the prediction bands that you computed when you were running the prediction itself. So if we do that, basically, um, we can basically plot again. So here, what you can see here with plot run size run time is a typical plot that we have done. And then what we can do is use the command matlines to plot the prediction bands, okay, the PP, which is called the prediction bands, and then we also created the confidence bands, which we use with matlines again. Okay, so remember that to plot the confidence and the prediction bands, what we need to do is to input the new data frame and the predicted values for that data frame. Okay, and again, an important observation here is, as you can see, the prediction bands represent a much wider area than the confidence band. Okay, and then finally, I also wanted to mention something. You can practice this at home, but basically, whenever you want to work with multivariate predictions, the LM function basically needs to get those inputs with the plus sign. So if instead of just one independent variable b1, you have multiple, you could write it that way.